Redox reaction and standard reduction potential. Any chemical equations in which electrons are transferred from one atom to the other are called redox reaction. Any substance that gains electrons, we say it undergoes reduction. Any substance that loses electrons, it undergoes oxidations. They cannot happen without one or the other. They have to happen together. Reducing agent is the one that reduces others, and itself is being oxidized, so it loses electrons. Oxidizing agent oxidizes others, so itself is being reduced, and it gains electrons. You may ask, how do I know if a chemical reaction is a redox reaction? Well, you can assign each substance its oxidizing number, which is the actual charge of monatomic ion. If the oxidation number changes during the reaction, then the redox reaction has taken place. Here is an example of redox reaction. The silver ion is being reduced because it gains one electron to become silver atom. And the silver nitrate is the oxidizing agent. Remember that oxidizing agent and reducing agent are the two terms that used for the entire formula unit. And the nitrate actually was included in the molecular equation. However, since this is the net ionic equation, we eliminate the spectator ions, which doesn't play any role in the reaction. And in this case, nitrate is the spectator ions. And copper is oxidized because it loses 2 electrons to become copper ion. And the copper is the reducing agent. Also notice that chemical reactions or chemical equations has to be balanced according to mass and charge. So since silver ion only gains 1 electron here, so we assign 2 as a coefficient for a silver ion to be able to gain 2 electrons, and it will have the same number of electrons lost by the copper. Then the chemical equation is balanced. Standard reduction potential is the potential or voltage of the reduction half reactions under the standard condition. The standard condition for a voltaic cell, which is a device that is generated by spontaneous redox reaction, is at 298 kelvins for temperature, 1 atmosphere for pressure, and 1 molar of concentration for all solutions. The standard reduction potential tells how easily or hard an oxidizing agent can be reduced. It has a unit of volt. The greater the value, the reduction potential, the easier it is to be reduced. So, for example, the fluorine has the highest reduction potential, so it is the easiest to be reduced. However, you cannot say fluoride ion is the easiest to be reduced, because reduction is the gain of electrons. And when electrons and fluorine are on the same side, they are treated as reactants. So we can say fluorine gains 2 electrons to become fluoride. And if you reverse the reaction, that will be fluoride ions loses 2 electrons to become fluorine. The hydrogen ions is reduced to become hydrogen, and it is defined to have 0 volt as the cell reduction potential. Lithium ion is the hardest to be reduced because it has the smallest reduction potential. However, lithium is the easiest to be oxidized because it is willing to give its electrons away. So notice that fluorine is the easiest to be reduced, while lithium is the easiest to be oxidized, and they are on the different side, opposite side of the reaction. The activity series is a list of metals in the order of their strengths to be able to be reduced or oxidized. These are the reduction potential. So the metal with the smallest reduction potential is the most reactive, which means it gives away its electrons easily. The metal with the highest reduction potential is the least reactive, which means it likes to grab electrons. So we can use activity series to determine if a single replacement will happen or not. So for example, the iron react with copper to iron. To see if it will happen, we can see iron has the smaller reduction potential than copper, so it is more reactive than copper. So this reaction will occur because iron would like to give its electrons away to copper ion to reduce it. However, the reverse of the single replacement will not occur because the less reactive copper will not give away its electrons to iron to reduce iron. We can compare the two metals of their ability to be oxidized or reduced by others. To do so, we have to first identify if it is an oxidizing or reducing agent. Why is it so important? Because oxidizing agent is on the left side of the reaction, and you will know that reducing agent is on the right side of the reaction. Then so after you know which side to look at when you are searching the reaction, you can just focus on that side. So you can choose the correct half reactions that contain the reagent that you are looking for on the correct side. And after you have the correct half reaction, you're actually comparing the reduction potential. Don't try to flip the number or add a negative sign on it, because when you do so, you're actually changing the reduction potential to oxidation potential. So when you compare two things, you really want them to be on the same basis. If you're comparing reduction potential with oxidation potential, then it's really hard to compare. And this is the chart that I made for the comparison of oxidizing and reducing agent. So if A can oxidize B, then that means A will grab electron from B to oxidize B, right? Then reduction potential of A will be greater than B. And if A cannot oxidize B, then the reduction potential of A is less than reduction potential of B. This statement is just the reverse of the previous one. If A can reduce B, that means the reduction potential of A is less than reduction potential of B. Because if A wants to reduce B, then A has to give away its electrons. And B is the one who gets the electrons at least. So B has to have a greater potential. And if A cannot reduce B, the reduction potential of A will be greater than the reduction potential of B. The same reason here. It is the reversed statement of the previous one. So the sign you just flip the sign. So make sure you understand the reasoning behind them instead of memorizing them. So here are some examples that we can do to apply what we just talked about. The first question is iron 3 capable of oxidizing iodide ion? Well, the first thing you need to do is identify the role of each substance here. So iron 3 is the oxidizing agent, so you'll immediately know that it's on the left side of the reaction. While iodide ion is the reducing agent, so it is on the right side of the reaction. And after you know which side, you can easily get the reaction from the reduction table. So here they are. And the third part is to compare their magnitude. And since the reduction potential of iron 3 is greater than the reduction potential of iodide ion, so yes, iron 3 can oxidize iodide ion. And the second question is iron 2 capable of reducing chromium 3 to chromium 2? Well, 2. The same process here. The first thing we need to do is iron 2 is a reducing agent, so it is on the right side of the reaction, and chromium 3 is the oxidizing agent. Because it is being reduced, so it is the oxidizing agent, and it will be on the left side of the reaction. So when you look at the reduction potential table, you'll find that two reactions both contain iron 2 in their half reactions. Then that's why I emphasized to be able to recognize which side of the reaction you have to know. And since iron 2 is the reducing agent, it's on the right side of the reaction. So we only need this reaction. We don't need this one. So we just compared this and the half reaction of chromium 3, which is really easily to pick. Okay, so now we compare the two values. Since reduction potential of iron 2 is greater than the reduction potential of chromium 3, the iron 2 will not reduce chromium 3 because iron 2 has a greater potential, then it will actually grab the electron from chromium 3. It will instead oxidize chromium 3. So, the second type of question here is the question will give you a lot of different kinds of substance. So the first thing you really want to do is to list all the half reactions from the potential table that contains each substance, no matter it's on the right side or left side. Just list all of them, including their potential value. So let's see the first question. Which is the strongest oxidizing agent? Well, you have to know oxidizing agent loves to grab electrons because it oxidizes others. So it has the largest reduction potential. So we can see that the largest one is this one. And we also know that oxidizing agent is on the left side of the reaction. So bromine is the strongest oxidizing agent. Which is the strongest reducing agent? Same process. Reducing agent loves to give its electrons away because it reduces other substances. So it has the smallest reduction potential. So the smallest one here will be this one. And since reducing agent is on the right side of the reaction, we know that calcium is the strongest reducing agent. Okay, the last type of question here. To pick a reagent that can oxidize manganese to manganese 2, but not oxidize nickel to nickel 2 ion. So first thing we need to do is to find the potential value of manganese. So we can find it from the reduction potential that it is negative 1.18 volt. For a substance to be able to oxidize manganese, the reduction potential of the substance has to be greater than manganese because it has to be able to grab electrons from manganese, so it has the greater potential. And since it cannot oxidize nickel, it has to have a smaller reduction potential than nickel does. So any oxidizing agent, it's on the left side of the reaction, so you just need to pick any agent that is on the left side of the reaction. And that with reduction potential in between negative 1.18 volt and negative 0.28 volt. Any reagent falls between the range will meet the requirement. An example will be cadmium 2 ion. For a reagent to be able to reduce silver ion to silver, but not reduce oxygen to hydrogen peroxide, it has to have a smaller reduction potential than silver does, which is 0.799 volt. And it has to have a larger potential than oxygen does, because it cannot reduce it. So, therefore, any reducing agent, which is on the right side of the reaction, with reduction potential in between these two values, will meet the requirement. And an example will be iron 2 ion. Finally, I just want to tell you that it's not complicated at all, as long as you think about it and you will know the answer. And congratulations!